Al, before you do the introductions, I just wanted to welcome everyone to the first chronic disease lecture for the 2021 new year, and to wish everyone a healthy and safe new year. And Dr. Begg, Dr. Nugent will be giving the formal introductions, but also just to remind everyone, we do have a 1 p.m. Faculty meeting. So I think if we could start soon, that would be great. We have 40 people on already. I know we're going to get many more because Dr. Begg, you're everyone, because you're a rock star, everyone wanted to come on. So thank you so much for doing this. And Dr. Nugent, thank you so much for inviting Dr. Begg.
Mm-hmm. Well, I'm delighted that Colin was able to join us. Colin is well known here, both in his own right and his spouse, but Colin has been the chair of biostatistics at Memorial Sloan Kettering for many years, and he's an outstanding biostatistician and both an outstanding practitioner of biostatistics and has made many contributions in the field. He also is the editor-in-chief of journal Clinical Trials, which is now a major journal in the field. I saw an article by Colin early this year, actually now it's early last year, on the subject of p-values and the use of p less than 0.05, and I've been thinking a lot about the issue of when do we have to stick to p less than 0.05, and particularly in observational studies, when are we being looser about its utilization? What do you do when it's p 0.06, et cetera? And I think this has become a major issue in our field in general. And Colin's article was actually more conservative on the subject than I anticipated, or than I thought the field was moving. I actually called Sharon Schwartz about it, and she was, I won't even say what she thought. She can speak for herself if she's on the line, but I thought then to invite Colin to come and talk to us about it, reflecting on his paper. So thanks, Colin, for coming, and I'll let you speak now.
Thanks, Al. And just I appreciate the invitation. I'm happy to be here. In response to what Mary Beth said, I doubt that my talk will take more than about half an hour. So you should all make your faculty meeting, and there should be time for discussion at the end of this. Actually, as I'll be pointing out later, the controversy about p-values has been around for quite a long time, but sort of the recent focus in this area was stimulated by an article that was published in Nature, actually almost 2 years ago now, by Ammerhein, Greenland, and McShane. What you see in the screen is a cartoon from the article, and you can see the investigator, the doctor, I guess, getting into the room, and there's all sorts of quack medicines up there in the shelves. And the sort of message from this cartoon is that the literature and our knowledge base is flooded with false positive results, and as a result, quack medicines. The stated goal of this article was to quote, retire statistical significance. The authors didn't really say too much about what would replace it, although they made a sort of passing reference to compatibility intervals, which they kind of described as essentially confidence intervals interpreted in a way that avoids overconfidence. Not entirely sure what that means, although I will return to the issue a little bit. Interestingly, I think that a lot of the people who have been concerned about overuse of p-values over the years it's been my sense, they've been concerned about what seemed to be displayed in that graphic in the previous slide, the notion that people use lots and lots of p-values. The way they're used in such a way that many of the studies that are claimed to be statistically significant are really false positives, and so the literature is flooded with false positive results. But interestingly, in this particular article, the authors they spent more time discussing the converse of that, which is that many authors interpret a non-significant result as a complete absence of effect. And they went on to coin the term dichotomania, which it seems to be used quite a bit now, which is a kind of a tendency for investigators to regard a statistical test as kind of a litmus test. It's either positive or negative. If it's positive, the theory is true. If it's negative, the theory is false. And that this sort of detracts from the nuance of interpretation of scientific findings. Now, this particular article caused a big stir, and it wasn't so much a stir in the lay press. It was more a stir among scientists, particularly bench scientists, who for whom it was kind of news that p-values might not be an ideal thing to use. And in fact, I think many of them interpreted it as a message that academic statisticians didn't really support statistical methods at all. And in fact, such was the blowback about this that we at our institution at Memorial Sloan Kettering, we felt the need to actually have a town hall, which was attended by hundreds of bench scientists wanting to know what all this was about. So the article really had a big impact. I want to take you back about 40 years at this point to a much earlier issue. This is an article from the Washington Post, March 21st, 1981. And the article was entitled Coffee, Tea, or Paranoia. And I'm just going to take the liberty of reading the article. It's very short. I've just poured a cup of coffee. I've powdered it with a sprinkling of sweet and low and laced it with a touch of anxiety. A little something for the pancreas, I say jocularly to the person behind me. I stir my coffee and put the lid in it. The word brew comes to mind as I carry my morning drink back to my desk. This week, I'm conscious of something more sinister in this cup. You see, coffee has been implicated. Nothing absolutely positively certain, just the inkling of a link between coffee and cancer. But it's enough to make Dr. Brian McMahon, the Harvard scientist who headed up the coffee research, give up the stuff. Enough for the rest of us to look deep into the black heart of the styrofoam container. I have here the abstract from the article that stimulated this that was published about 10 days before that Washington Post article. It was published in the New England Journal, and it was a case control study with, I think in the modern epidemiologists would look at this and say it's sort of a charmingly small sample size. There were only about 370 patients and twice as many controls. The authors had looked at a bunch of risk factors, some of which are listed in the abstract, but honed in on a strong statistically significant trend test between coffee drinking and cancer of the pancreas, and quoting a p-value there of 0.001. Now, you know, I realize I'm kind of acknowledging my age here, and probably many of the people in the call, this is way before your time, but I can assure you the public outcry about this article was just astounding. I mean, everyone drinks coffee. Out came the news that if you drank coffee, you were going to get cancer of the pancreas. It caused a sensation. And you know, sadly, but I was at Harvard at the time. I was a professor there, and I knew Brian McMahon. I'd worked in doctoral committees with him and stuff. Nice guy, great scientist. But this episode actually really damaged his career, because it was quickly debunked, perceived to be really an inappropriate publication and an overstating of the evidence. But in fact, it really was a forerunner of a generation of research into nutritional epidemiology of cancer. And over the next 20 years or so, we saw countless articles like this coming out, linking individual foodstuffs with, well, you name what cancer you can. And many of these articles were published in the New England Journal and other prominent journals like that. Now, let me say that. Okay, so let me just move on here, and I'll get back to this issue. I also, you know, that was 40 years ago, but I want to make an important point here that the issue about p-values and the appropriateness or not of their use has really been around for a long time. I was personally educated in the early 70s. That's when I did my PhD, and the academic department in which I was educated was a department that really were promoting Bayesian methods at that time, and they were strongly discouraging the use of p-values even back then. I remember one of the course professors would taught his course and basically was encouraging us all to use what he called intervals of strong evidence, which actually bears a very similar resemblance to what the Amrahen article were promoting. I actually emerged from my education in statistics without really knowing what the analysis of variance was, because of the strong emphasis on Bayesian methods. But unlike many people nowadays, I emerged into the workforce and kind of actually came to believe that p-values were actually okay, and there were more problems with the Bayesian approach than there were with traditional statistical methods. Now, around that time, or at least the late 70s, early 80s, there was another article that caused a lot of fuss, and that was an article published by Ken Rothman, also in the New England Journal, 1978, in which he said, you know, p-values are the source of all ill in scientific reporting. Interestingly, Rothman was a PhD student of McMahon, and he was strongly opposed to the use of p-values at all. And in fact, he subsequently became the founding editor of the journal Epidemiology, which of course is still around today. And he banned the use of p-values in this journal. Interestingly, there's been a couple of other journals in the recent past who have done something similar, but that trend didn't really catch on. Although, interestingly, the New England Journal has very recently provided new guidelines on reporting of results. And I've summarized some of the guidelines here that correspond to observational studies. And they are, in fact, don't want to see p-values for observational studies without a statistical analysis plan. And they provide very detailed instructions about how p-values can be used for clinical trials. Interestingly, another thing that occurred in the last few years that's relevant to this discussion was that the American Statistical Association actually took it upon itself to come out with a statement on p-values, which was kind of broadly critical of p-values. That was published in the American Statistician in 2016. Anyway, my point here in all of this is that people have been arguing about p-values and their appropriateness for really a long time, generations before the recent fuss that stemmed from the Amrahen, Greenland, and McShane article. Now, it's interesting. I've seen all of these opinions raised over the years, and they've generally been promoted by people who are critical of p-values. But it occurred to me when I got engaged with this, particularly for the talk we had to give to our lab scientists at Memorial, to actually give some thought to why p-values are so popular. Because, you know, p-values are really ubiquitous in science. They must be probably the most used scientific tool of all time anywhere, in any field. They're incredibly widely used, not only across science, across everywhere where data analysis takes place. So why are they so popular? And I've listed here what I think the reasons are. First of all, it's just an extraordinarily versatile framework for making a scientific inference. You know, it's also extremely simple. So you can take any test when you're testing an effect under any circumstances, whether it's a test of binary outcomes, survival data, any kind of data. If you're doing a test that emerges from a regression model, pretty much any setup where you're trying to compare two different categories, you can summarize the evidence in this thing, the p-value, which is a single metric, and it has the same meaning under all of these different frameworks. Now, that simplicity is really the source of its widespread use. Now, the people who have argued against the use of p-values have often argued that a problem is that users don't really understand the p-value. They don't understand what it means. They make mistakes about it. So I've listed here some of the reasons they've given, that some users interpret the p-value as the probability the null hypothesis is true. The interpretation that non-significance means that the null is true, which is in fact the main thesis of the Amrhein article, as I mentioned earlier. There's also been arguments that the null hypothesis can never really be true literally, it's just an approximation. I really don't think these arguments really hold much water or are particularly important. Users may not understand the exact technical details of the p-value, but they truly do understand what its purpose and its role is. It's a simple litmus test for testing a hypothesis. If p is less than 0.5 or whatever, the test is positive, and if it's not, it's not. So in other words, my point here is that users use the p-value because they really do understand its purpose, at least in the context of what they are trying to do in interpretation of their data. Why are p-values so unpopular with some academic statisticians? Well, there's really two sort of groups of reasons here. What I consider non-substantive reasons, which is that non-statistical users don't really understand the meaning of a statistical test. I've just explained in the previous slide why, well, there might be some truth to that. I don't really think it's that important. A much more substantive reason is that the use of p-values leads to bad scientific practice. In other words, that encouraging people all over the place to use p-values leads to the kinds of problems I alluded to before. We flood the literature with false positive findings. People misinterpret the results of their studies. That is a substantive reason to be concerned about p-values. And there's no question that both of these criticisms are true. I mean, I don't have any doubt that the literature is flooded with false positive results, and that people are inclined to use statistical tests in a way that encourages that. I'm certain that what Amrhein described about the misinterpretation of non-significant results as proof of no effect is also true. I mean, you see many authors make that mistake all the time. But the real question here is, would things be improved in the absence of statistical testing? What would replace it? My answer is no. I do think there are problems with the way scientific results are interpreted and promoted, but statistical testing has pretty much nothing to do with it. And that will be the thesis of what I talk about for much of the rest of the talk. what are the ingredients of a good study, a valid scientific experiment? And so I've listed here some suggestions, and if you want to conduct a study that's likely to be replicable, you define clearly the endpoint up front. You specify the study population that you're going to investigate. When you come to analyze the data, you have to be concerned about elective exclusions. You know, examination of subgroups, particularly if you're rummaging around looking for subgroups where the p-value is significant, is problematic. If you look at the individual data points and throw out the ones that don't seem to fit or don't seem to fit your hypothesis, well, that's going to lead you astray. You know, another positive feature of a good study plan is to have a predefined statistical method. You shouldn't have the option to look at lots of different statistical methods or different tests, different ways of adjusting factors, and electively run your way through all these analyses in order to find the one that seems to fit your preconceived thesis. Now, in fact, all of these things correspond to protocolized research, basically. And in fact, for those of you who are engaged in clinical trials, you'll know that a high quality clinical trial has a very carefully defined protocol that meets all of these criteria that I have just described. How much of reported scientific work in the literature is protocol driven? Not much, I would say. And in fact, typically in the literature, what we read and what is described could better be described as exploratory research. Exploratory research is particularly pertinent in, frankly, in epidemiology, you know, where often as not, the studies that are conducted involve collection of lots of data. While there might be a primary goal of the study in the first place, many of the publications that come out at the end of the day are exploratory, of an exploratory nature, where you look at individual risk factors and the like that have been collected as part of the study. And so if you just apply statistical testing in this context, the validity is not going to be as described in statistical textbooks. But that's true of any statistical method you would use, not just the use of p-values. Now, I want to make the point here that, and I say this, you know, Al introduced me as a statistician, but in fact, I consider myself an epidemiologist too. I've led primary data collection studies myself, and I know very well that when you conduct a study, you start with a theory, and you're personally, emotionally committed to the theory, and it's exciting. You know, you have this idea of how the research is going to work out. You go to the trouble of collecting all the data, and you hope very much that the results will fit your preconceived notions. And it's almost impossible to resist the temptation to explore the data and to interpret it in a way that fits with your preconceived notions. I mean, that's just the human factor and how it plays into science. And I think that the problems we face in the reporting of scientific information is much more dependent on this human factor and the proclivity to believe our own theories than anything to do with the use of p-values and statistical testing. Now, science nowadays, much more so than in the days of the coffee and pancreas cancer paper, even although clearly it was happening back then, nowadays, we really live in a culture that has changed a lot. And it's a culture that rewards the exaggeration of scientific findings. In my opinion, the culprits for this are the lay press, who are much, much more engaged in reporting scientific findings than they were a generation or two ago. And just by the nature of their game, they want to hype up the results they're reporting. Public relations departments of academic institutions didn't exist a generation ago. Nowadays, all the big academic institutions have them. They encourage the people, the investigators in their institutions to have press releases and the like before articles appear that might conceivably be published, covered by the lay press. I can certainly remember when I was growing up, so to speak, in academic life, that it was quite openly frowned upon to be seeking lay publicity for your scientific work. Nothing could be further from the truth nowadays, and scientists all over the place really go looking for publicity, and they do it actually, to be perfectly frankly, in the knowledge that it helps their academic career, because name recognition actually helps and works to advance your career. And also, you have to wonder about some of the leading academic journals, about the articles that they publish, because it certainly seems to me that a major factor influencing what they publish is the extent to which it will garner press attention, even if the solidity of the findings are suspect. So this is just a cartoon that kind of describes what I've just been talking about. We have this milieu nowadays where there's these pressures for scientists to make out that the individual results of the studies are more important than they really are, or more solid. It's driven by this culture that is a mix of the incentives of the journals, the institutions who want to raise money for research, and the perception among academics that name recognition helps your academic career. And this all feeds into a culture which degrades the replicability of the research findings from published results. Well, so what do we do to make the scientific process more credible? I think that some of it is happening, to be perfectly honest. I'm sure many of you are aware that there's been a big focus over the last several years on the notion of reproducibility and replicability. The NIH has paid a lot of attention to that. And in fact, there was a paper by Francis Collins published in Nature a few years ago calling on lab scientists in particular to be better trained in study design and statistical analysis, and the perception that that would improve the process. I think that the kind of transparency revolution is extremely important, because when people publish results, it's really hard to be critical of them in an informed way if you don't have access to the data and methods that drove the study. And often as not, the papers themselves don't provide key details in that respect. But there's clearly been a big movement in recent years to allow other scientists to have access to the data and methods from published studies. And in fact, some major specific initiatives that have taken place really over the last generation have moved us in this direction, include the registration of clinical trials. And nowadays, clinical trials have to be registered before they are published, before they're started, in order that the trial be published in the major journals at the end of it. And the whole point of this is in part so that when reviewers look at the eventual submitted paper, they can actually compare what the authors claim they did to what they said they would do in the study protocol. There are reporting guidelines for clinical trials and numerous other kinds of studies, case control studies, meta-analysis and the like, that are now part and parcel of what's expected of people when they published findings. And in the last few years, much more of a push towards publication of raw data, which allows interested scientists to go back and actually redo the analyses of studies that have been published where they may be skeptical about the results. It's my opinion that these are the innovations that will ultimately improve the quality of scientific inferences, and that fretting about statistical testing is just a minor league issue on the shores of this concern. I want to draw your attention to a paper that was published now really 50 years ago. It was actually a broadcast by the BBC by Sir Peter Medawar, who was a Nobel laureate, who was well known for educating the public about science. But he published this famous lecture called "Is the Scientific Paper a Fraud?" And for those of you who are interested, I would encourage you to go back and read this. It's not that long. And basically, what he was criticizing, he wasn't implying that scientists are all fraudulent. He was criticizing the way in which we report scientific findings in the classical introduction, methods, results, discussion style of an academic article, which is still in play to this day. And what he was really getting at is that when you read a scientific article, what you read is a kind of a logical, linear narrative of what happened. We had this hypothesis, we did this, we got this result, and we drew this conclusion. But other than for a perfectly followed randomized clinical trial, for all of the kind of exploratory science that comprises over 90% of the published literature, what you read in the article is really a highly sanitized version of what actually happened. It doesn't report all the false starts, the changes of opinion, and all the other things that take place as discovery science moves ahead. And as a result, when you read the article, you just don't get a feeling for the true nature of the scientific process, and that in interpreting the results of a study, you kind of need to know all of this other stuff, especially with regard to the selectivity of the data as they are presented in the article. And in fact, I think 60 years on, this article really looks very modern to me. It looks like a plea for transparency. And this is a cartoon that kind of captures what I think of as a scientific method. And I want to draw your attention to the top half of this article, of this cartoon, and the bottom half. In the bottom half, what I think is what people think of as a scientific method, where you have a precise hypothesis, you set up a protocol to challenge the hypothesis, you collect data, do the study, publish the results, and draw your conclusions. And if you follow the kind of rules I described earlier that characterize a protocol, then you're following the scientific method, and there's a good chance that if you take all the right steps, your results will be replicable. And if you have a positive result, there's a good chance it would be replicated in a subsequent experiment, and so forth. But that really, the bulk of science takes place in the discovery phase, which is the top half of the diagram. And that's a much more exploratory environment. And in fact, that's the exciting part of science. That's what turns people on. That's what makes it interesting when you're getting data from lots of different sources, forming your opinions and your theories. That's the exciting stuff. And often as not, that's what ends up in the journals, but it really isn't the scientific method, or it doesn't conform to the scientific method as we understand it. Now, I want to say that there's kind of a view. There was another paper published. Sorry, I didn't cite it here. There was a paper published in response to the Collins article I mentioned earlier by a group from the National Academy of Sciences, and they argued that in fact science really works quite well because it's a self-correcting enterprise. You know, a scientist publishes a result. If the result isn't correct, some other scientist will come along and show that it isn't correct. And that self-correcting network is, in fact, the strength of the scientific method. And so, you know, you have this system where you discover some hypothetical finding. You publish it in a transparent publication. There are replication experiments that either refute or confirm the findings. And if they could refute them, you have to go back to square one and revise your theories. Unfortunately, I think this system really doesn't work efficiently at all for the reasons that are highlighted in red in this follow-up slide. First of all, most scientific advances are not path-breaking, and so there just aren't a whole team of people out there in other labs prepared to take the time to do a replication experiment to back up findings. The absence of transparency hinders the ability to really fully investigate the published article. But perhaps more importantly, that there really is a very, very poor reward culture for replication of other people's studies and for criticism of other people's studies. I can tell you that I have in my career more than once taken the trouble to actually publish an article criticizing a previous published article openly because I thought it was important and necessary to do that. And I can assure you, you make no friends whatsoever when you do that. And I think many scientists know that nobody wants to be criticized. And so the process of open criticism really doesn't happen at the level that it ought to do because it doesn't benefit your own scientific career. Furthermore, to go and replicate somebody else's experiment or do the work to figure out if they're right or wrong is a major process. It's very costly and it takes you down a path which is not original. And so it's just not clear that it really helps your individual academic career very well. I just have a couple more slides. I want to just mention the process of drug approvals because, you know, when we talk about p-values have really played an important historical role in the evaluation of drugs by the FDA. The traditional FDA approach to evaluating new agents was that the sponsors had to do 2 pivotal randomized trials and that both had to be statistically significant at the 5% level. And this is an extraordinarily rigid system and has, you know, been criticized for many years as being just sort of very overly rigid. But you have to ask yourself, why did the FDA do this? Why did they set up rules like this? I don't think it was anything to do with a great love for p-values and the arbitrary nature of the statistical test. The reason they were doing it is because of this human nature issue that I brought up earlier. When a drug company wants to, is seeking to get their drug approved, there's vast financial considerations there. I mean, the conflict of interest is just overwhelming. And so it's inevitable they're going to be shedding the results of the trial in the most favorable light possible for obtaining a drug approval. And so it's for these reasons that FDA demands a rigorously protocol-driven process for evaluating agents, and it absolutely minimizes and attempts to eliminate the human factor at any level by ensuring that the results must be really definitive. the whole purpose of this is really to offset the human factor and the incentives. It's not necessarily because of a great love for statistical testing. Interestingly, in recent years, the pharma landscape has kind of changed. The FDA has become much less prescriptive. They're much more willing to do expedited review, to approve agents without randomized evidence. Another concept, I'm not too thrilled about this if it's not too obvious from my tone of voice. There's another issue that is kind of relevant here is the penetration of industry into the academic world. You know, many drugs nowadays are developed in academic labs, and the inventor, an academic investigator, is very often has skin in the game when it comes to bringing the drug to market. And these conflicts of interest are you know, a huge issue in academic life these days, and they really were very different from what it was like a generation or so ago. Conversely, drug companies are strongly encouraged to make their data publicly available now, so that really is a positive thing. So to wrap up, my take-home messages are that it's an inherent part of the scientific process that scientists are human beings, and they have this tendency to use data selectively to support their thesis. That encourages them to present data in the best possible light. It's human nature, it affects all of us, myself included. And that when you do that, it tends to undermine the probabilistic basis of conventional statistical methods. This is true for anything, any method, not just statistical testing. I would also point out that scientists in general don't have the same reverence for statistical methods as statisticians do. So they're less concerned about the inaccuracies or poor interpretation of statistical methods. The tendency to exaggerate finding is further driven by contemporary celebrity culture, the pressures from academic institutions, journals, and the lay media, and also the embrace of academic research by the for-profit industry. What's the best defense in all of this? Well, I think transparency is a very positive trend nowadays. And we really need to re-emphasize among ourselves the truth-seeking mission of the scientific method. Thank you very much. Happy to take comments or questions.
Thank you for this very interesting and
I'm having a hard time hearing whoever's speaking. Could you speak up a little bit?
Oh, yes. Can you hear me now? Is that better?
Yeah, that's a little bit better, right.
Sorry about that. Yeah, I was thanking you. That's the part that you missed for this stimulating talk. And I was most interested by the comment that you made about the celebrity culture and the way of writing the article in a more sexier way. Often right now, I was taught that you had to write your title, you know, pretty independently, and now the result is in the title, roughly. So that's for the comment. The question I have is regarding the advent of big data and the accumulation of evidence. How do you see the role of p-value when we move to a world where we have big data and where perhaps it's more of a Bayesian accumulation of evidence that may drive implications? I don't know if you're hearing me or if...
Yeah, I hear you.
Yeah.
So, well, you know, big data, I mean, clearly we live in an era where there are much larger databases. There's lots of data resources out there that can be used for research. That's where we're at the moment. I would just I would say in response to your question, I've been focusing on p-values here because p-values are sort of under assault. It's by no means my intention to give the impression that every statistical analysis should be built around statistical testing and p-values. I don't think that for a minute. There are thousands of statistical methods out there that are much more elaborate and are well documented for validity if they're used right. And so anytime you analyze data, you use the methods that are fit for purpose. Clearly, when we're analyzing big data, the analyses often are more complex. But they're also much more susceptible to overconfidence and for making mistakes along the way that you may not even be aware of. So I think that any analyses that rely on observational data from existing databases, you have to be critical about the methods and circumspect about the conclusions.
Hi, Dr. Begg. My name's Natalie B. I'm a doctoral student in the Epi department. Thank you for a great talk. I found it really interesting. I will confess to being a person who has tried to avoid p-values in my work of late. And I was interested if you could elaborate a little bit on your statement that no standard statistical method will work well when we're doing exploratory analysis. If you could just explain a little bit more.
Yeah, that's not quite what I said.
Oh, okay. Sorry. I have that there's a low validity of any statistical method.
I think, there's nothing wrong with exploratory analyses. And in fact, what the point I was trying to make is that if you conduct an exploratory analysis, or even if you conduct an analysis of a randomized trial, but you start to do things like throw patients out that don't fit with your model or engage in subgroup analysis or whatever. If you do these things and you do them in a way that you're really searching around for findings that are conclusive, it's inevitable you're going to find them. The bigger the database, the more sort of degrees of freedom there are to look at things, the more likely you are to find extreme results. And so if you engage in the analysis, either intentionally or unconsciously doing that, it's inevitable you're going to get findings that are not as believable as the statistical method would have you believe. And my point was, that's true regardless of what kind of method you use. It's not just linked to statistical testing. It's true for any method you would use, that if you're searching for a strong result and you find the strong result through searching for a strong result, you're going to overestimate the confidence of the result.
Sure, that completely makes sense. I was wondering if you had any thoughts about the best methods that should be used for exploratory analysis, like especially in framing in the context of the rest of your talk. How do we do exploratory analysis well and in a transparent way?
Yeah, that's a difficult question, but I will say two things to this. One related to the very last point of my final slide, which is, the scientific method is truth-seeking in its ideal form, and we should be continually regrounding ourselves in our own minds that we're searching for the truth. We're not searching for a result that will get us the next grant or the paper in the New England Journal. We should really be self-critical about findings that we come across in our exploratory work. It's really, and that's where I'm addressing the human nature issue. And the other point I would make, which I also alluded to, is that I just don't think there's enough of a willingness in our scientific culture to be openly critical of results that are published. I think, and I kind of outlined the reasons why people steer clear of it, but I would much prefer to see a more active, openly critical environment where people publish results and others come out and say, no, I'm sorry, this just doesn't stand up to close scrutiny, rather than just sort of keep quiet because you don't want to make enemies.
Thank you so much.
Just a question, if I may, if there is no other. So some people, including Philippe Raveau, that I think you know, and Isabelle Boutron at CREST and the Cochrane Center, have advocated research on research, not so much talking about the fraud, which is a pretty clear-cut dichotomous most of the time, but not the fraud, but kind of the tendency to believe one's research and stuff like that. Part of it added, and you alluded to that point, with the fact that positive results are easier to be published than negative results. Do you think that, what do you think could be a solution? Should it be that there'll be a journal of negative results? There will be that the system of not having editors actually picking, but rather having a system of publication like PLOS, or where most things are published. I guess it seems to me that I'm not sure what the solution would be, and I wondered whether you had some thoughts about that.
Yeah, I'm not. I don't have a solution. Although I think that the modern trends to encourage transparency are actually quite useful here. You know, because if people publish their own data, at least there's the opportunity for others to get in there and be and engage in an informed criticism. In terms of how the journals work and what they choose to publish, I mean, it's that's I don't really know what to say there. I think that we still are very much in a system whereby scientist does study and publishes it as a discrete entity in a journal somewhere, that's how we transmit scientific findings for the most part. I don't have any good insights into how that could be meaningfully changed. I mean, I would love to see reviews better, but you know, the truth is the review system is flooded these days. There's so many articles, so much research going on. I you know, as an editor of a journal, just finding reviewers is a big challenge, and so it's inevitable that lots of papers will make it through without really having a very careful review.
Well, thanks, Colin. I think you did a great job. It was a pleasure to hear you, and I think it was a good kickoff to this semester's talks. And maybe we better let you off the hook while you still haven't made any enemies here today. And I know there's a faculty meeting coming up, and maybe people have to go to the bathroom. Am I allowed to say bathroom? Thanks a lot, and I think we'll let it go at that. Okay, Mary Beth, did I do okay? Okay, Mary Beth probably left.
Oh, sorry, no, I was on mute, but thank you so much, Dr. Begg. That was fantastic, and really appreciate your time today, and thanks again, and for this very provocative talk.
All right, my pleasure. Thank you.
Thank you,
Good to see you all again.
Yeah,
Bye-bye.
Thank you for joining, and we have a another talk next month, which you'll be seeing in your email. So thanks again.